today I would like to go over the acid-base titration analysis, but I can't do that until you've done your calculations. So when you get out your lab, and I realize that you probably likely didn't finish calculations, so you have a quiz to study for and stuff like that. So I wanted to give you just a few minutes to finish those up. And then the analysis part to go over is going to be just make a lot more sense. The analysis is similar to last time. Like, what would happen if, and you kind of have to like look at your calculations and figure out if the denominator gets bigger or the numerator gets bigger. So go ahead and finish your calculations. If you're done with your calculations, this yellow sheet is a test review for the test on this unit. You can work on that. Obviously, you have quiz questions if you want to do that. There's other stuff like don't waste your time and sit there. Do something, okay? Ready? Go. The sample is on Schoology, or I put it up here if you can see it. Okay. These three questions are going to answer your first two analysis questions, okay? So this doesn't match exactly what's on there because I'm like trying to baby step you into thinking about it, right? It's like a lot of layers of thinking, okay? So it says if the KHP was impure, KHP was what we put the first three titrations in the flask. So we did the 0.4 and put it in the flask. And up here in our burette, we had our chunky NaOH. And the first three titrations, the point was to figure out what the molarity of our chunky NaOH was because it was chunky. We tried to make 0.1, but it wouldn't work out to be 0.1. Okay? So what this is saying is if that KHP was dirty, it's just going to be. Sometimes I just can't buy super pure stuff. Like it just comes that way. How would that affect how much NaOH it would take to neutralize it to our eyeballs? That's when it turned pink. That's called the endpoint when it turns pink, but it's actually exactly neutral one drop before that at the equivalence point. Okay? So if our scale said 0.4 grams, but it was dirty, how much NaOH? Would it take less or more NaOH to neutralize it? Talk about that. I'm recording because I'm gone the rest of the day, so I can't play music. So you're just going to have to like pretend there's music and still talk. So talk about that with somebody. Higher or lower volume of NaOH to neutralize it. Ready, set, go. Yeah. Okay. Okay, you need that. Okay, would it take more or less? Okay. Now, though, this is what the actual question says. The first analysis question says, how would that affect the molarity of the NaOH? So that comes from volume of NaOH, you just decided. How does the volume affect the molarity? So go to your calculations and decide if it's going to make your molarity go up or is it going to make your molarity go down? Moles divided by liters. Does that make it go up or does it make it go down? Okay, write it so then when this weekend you're typing it, you know what to type. Okay, now the second analysis question says, how would that? So you made a decision on molarity. Now this is going to be hard. You're going to have to follow this a few different places. You made a decision on molarity. You said, okay, this number is either going to go up or it's going to go down, but all of you know which way it's going to go. How does that affect this way down here? The molar mass of the, bless you, The molar mass of the unknown acid was grams divided by moles. So we took this number and we divided it by this number to get that one there. But how does a bigger molarity affect that? Okay, so now you need to track this number. Where did you use your 0.102 or whatever that was? Make it bigger and see what happens to here. So that number went here first. Then that number went here next, because we had to do a mole ratio. And then that number went here. So this is going to take a little bit of thinking. If this number is bigger, how does that change that number? How does that then change that number, and then how does that change that number? Okay? Ready? Go. Talk that out and then write it down. Okay. We finished the lab on a Wednesday, which means that the lab is going to be due on a Wednesday. So the lab is going to be due next Wednesday. Also on Wednesday, we are going to take our Chapter 4 test. So we just took the quiz. We're going to go over that in a second. What I have for you up here is your quiz corrections. If you would like to get half your points back on your quiz, you need to do all of them. Stabilize your quiz. It's going to be due on Wednesday, the day of the test. So that means you're going to be turning in the lab and this and taking a test on the same day. So now in your head, you should be thinking about, hey, this weekend I should probably finish my labs because next week I'm going to be busy with other stuff. Okay? Next to it, can you get this out? Because I have to cut across the though. Next to it is a test review. Some people just like to have a couple extra practice problems to do, like right before the test. They usually do their quiz practice this weekend. Ones that aren't going to apply is number 7. Can you cross off number 7? Number 12. And number 15. And answers for this are posted. This is just a good test review. It's just one more question on each of the learning objectives for that. This was a divider because we are starting a new unit today. Our Chapter 5 learning objectives. For Chapter 5, we're starting today. It will go quick. Chapter 4 is our longest chapter. It will take us only between 3 and 5 lectures usually to finish a chapter. So plan on forever and always going a lot faster than we have been. So you have your learning objectives, you have your notes and sample problems, and then turn to your lab. So let's go over the quiz next. There's some things I want to tell you so you don't get them wrong in the test, okay? Some things I was lenient on the quiz, but I will not be lenient on the test. So I want to tell you that. For the first question, explain what happens to a strong electrolyte when it dissolves in a solution. You need to use the word dissociates. It was a vocab word, dissociates, and you need to have ions. On the test, I will tell you, you will be drawing a beaker. You are going to have to draw your beaker, and you're going to have to draw your, good timing. And we're going to have to draw your dipole with your water molecules and your ions and potentially like a pile of precipitate on the bottom, okay? So this question does not look like this on the test. It's going to be harder. You're going to have to draw a particular diagram. Number 2, what precipitate formed. See how I could combine those two? Because in your beaker, if it has a precipitate, you're going to have to draw it on the bottom with your name and label it and everything, okay? Oxidation number, this is kind of hard to see, is going to be +5 for this. Sodium is always +1. Oxygen is always -2 except peroxide. Pause for effect. The peroxide is always -1. So I have 3 oxygens, each at -2, so that's -6 altogether. My sodium is +1 to add up to 0. That means it has to be +5. Okay, number 4. Every single person would get this wrong on the test right now. So if you got it right, you're not right. I just wasn't going to mark every single person's wrong. You cannot use a location on a random list as a reason, okay? I know that manganese is higher than nickel or whatever you said is higher than the other, but what if you were given a chart that was just flipped the other way? That chart is just arbitrarily highest to lowest. You have to use the words more reactive then. You cannot earn a point by saying a location. You have to give an actual scientific reason. It is higher, but on that chart, higher means more reactive, okay? If you say higher or lower on the test, you will not earn the point. This is only one time, because I never told you that. For your dissociation problem, the ratio is 1 to 3. There's multiple ways you could have shown me this. Essentially, you just need to solve for molarity. Moles divided by liters. Some of you did your mole, Some of you did your mole ratio first, and you had the 3 times. Come on. And then it worked out to be in the same, but some of you did it after.
Good morning. Can I have a great day?
Can I have my tea?
Oh, did you want that today? We can get you one.
No. I pay it next week. I think.
I know.
Okay. So you have to multiply it by 3 because you have a mole ratio of 3/1. And then this one is just going to be the same. Okay. Number 6 is your only dilution problem. The only time you can do M1V1 equals M2V2, if it says diluting, that's a dilution equation. It's a proportion because it's the same stuff. I'm taking sodium hydroxide, I'm just adding water to sodium hydroxide. Okay? Number 7. I tried to tell you that this is not going to be baby chem or honor chem converting. You have to be able to convert anything to anywhere. So always start with your volume, except for when that's what you're trying to solve for. Milliliters to liters, liters to moles, moles to grams. It's okay if you did it in multiple steps. You can do that. If your brain works that you want to do it in 4 different things, then do it. That's fine. Just watch your rounding, because sometimes if you like only round it to 1 sig fig, then you will never end up at this answer eventually. Okay? Spectators are your potassium and your nitrate. All nitrates are soluble. Anytime we have an acid-base reaction, our net ionic is always going to be the same thing. Okay, let's look at our titration problem. We have nitric acid, we have sodium hydroxide, 31.5 milliliters of the nitric acid and 23.9 of a 0.0314. Do your flow. Milliliters to liters, liters to moles. When we are at moles, our next step is a mole ratio. Moles to mole ratio. So if you did not have a mole ratio, you do not earn a point. I know it's 1-to-1, but if you don't do a mole ratio, you're solving for the wrong thing. So you have to have your mole ratio, and then we stop there because we're not solving for grams. Moles divided by liters gives us a molarity. It's fine if you did it in multiple steps. You could totally do that. Just watch your rounding, okay? Number 11 feels different because we're starting at moles. But just always start, and just if it says moles on top, then put moles on bottom, and think about it. Okay, when I add moles, my next step is always mole ratio. Moles to mole ratio. Once I'm here, then I can do my molarity and then convert it to liters. You don't have to do it that way. You can do it all in different steps. It's totally fine. But make sure you have a mole ratio. Okay, do you have a question?
I would put like X moles over liters equals the molarity and then like solve it that way.
Yeah, that's what I said. You can do it all in separate steps, so something in your math might not have been right.
No,
I can
you
come.
mark it wrong.
Oh, yeah, that's what I said. You can do it all in separate steps if you would like to. Just watch your rounding if you're not all going to do it the same flow in your
I just
calculator.
asking like to type of math. I like the way that I wrote it was different than like England.
Yep.
Okay.
That's what I'm saying.
Okay.
That's what I mean. You can do it that way. Okay. So, quiz corrections and this, correct it, staple it together, give it back to me on Wednesday. I'll give you half your points back. Test on this stuff is going to be on Wednesday. Honestly, the test isn't that much harder because we haven't learned anything hard yet. Like, how many ways can I ask you to write an ionic equation, right? It's like pretty much going to be the same. Don't forget that beaker particulate diagram will be on the test for sure. That is the one thing that I didn't have you do on the quiz. That'll be on the test. Okay? So you can go ahead and put that all away and get out your notes. We are going to start our next unit. All right, chapter 5. Chapter 5 is on thermodynamics. For most of you, this is all going to be new. If you took physics, some of the vocab words, or AP physics especially, yeah, we are using colors today for sure. So blue and red, we're going to draw a graph with blue and red for sure. And I feel like you're going to want a highlighter at one point, so while you're getting stuff out. If you have not taken physics, you'll be fine. You'll just be learning the words for the first time. Okay, thermochemistry is how physics and chemistry go together. For this unit, it's just like kind of a basic overview, and then at the end of the year, we come back and do it a little bit more robustly. But mostly everything, if you look on the posters on the wall, is going to be completely foreign to you. The one equation that you did do, I think, in honors chemistry, and maybe even in basic chem, is the Q equals MCS delta T equation. Yeah, I'm not sure that you know even any of this. So this is going to be our first unit that everything's going to be new. You'll be fine. Okay, so energy. Energy can be two things. It can either be kinetic energy or it can be potential energy. Kinetic energy is the energy of movement. So in chemistry, the kinetic energy comes from the movement of the molecules. And when you're done, you need to get your molecule hands out. So a solid is doing this. This is the movement. Use your molecule hands. We also have cheerleading hands. We have lots of hands. These are your molecule hands. This is the movement. This is the kinetic energy. In a liquid, it's moving. Do it. It's moving a little bit more. Exercise is good for learning things. This is the kinetic energy. In a gas, they're moving a lot more. Okay? Very good. The movement of molecules, the kinetic energy equals the temperature, is related to the temperature. The faster they move, the more kinetic energy they have, the higher the temperature. The slower they move, the less kinetic energy they have, the lower the temperature. Okay? The potential energy comes from the pushing and the pulling of the magnets. I called it clicking and boinging, but like it's actually the pushing and the pulling. So without getting the magnets out again, so kind of think back in your head. When you took two magnets and you held them close together and they were attracted to each other, they moved, right? They boinged together, they clicked together. The point at where you're holding them, but they're not moving yet, is the potential energy. In physics, we say there's a ball at the top of the hill. It has the potential to roll down the hill. I don't have to do anything to it. It's just going to roll down the hill. If I take two magnets and I hold them together, if I let go of them, they just move. I didn't have to do anything. That's potential energy. But same when you boing them. So if you put them in there pushing apart, if some of you are doing this, you hold them together and then you let go and they boing off. That's the potential energy. So the pulling is because positive part, negative. The attraction, I don't have to do anything. It has the potential to move. The pushing is the repulsion. Negative hates negative and positive hates positive. When the music starts, you're just going to talk to your battle buddy about the two types of energy. So just because you wrote it, just because you heard me say it, does not mean that you learned it. So good learning would then be you talk about it, which might be because this is pretty simple. You might just be able to talk about it. For harder things, you might just be like reading what you just wrote down. But you need to talk about it and you need to hear it to help you learn it. So ready, set. Okay, units for energy. They are called joules. We do not have a joule-o-meter. We cannot measure energy. We can only calculate it. So we're going to do a bunch of different ways to calculate energy. Okay. I have a thermometer. I can measure temperature, but there isn't some way for me to measure joules. So we are going to calculate in a bunch of different ways. Okay. This is what I thought you might want to highlight. This little conversion factor is going to be super helpful. We need everything to be in joules, but sometimes it's given to us in calories and we have to convert it before we can do anything with it. The conversion is 1 calorie equals 4.184 joules. Just as a side note, our food calories are actually 1,000 science calories. Except if you're in anywhere else in the world except the United States. So like a Coke has 180 calories, I think. On the can for in the United States, it's actually 180,000 calories, like a science calorie. And if you go into Europe, it'll say 180,000 on it. So it's just us. I think they think that we can't add big numbers or something, so they change it. Okay? I don't know. That random fact shows up on the AP test every once in a while, so keep that in mind. All right, so kinetic energy is the energy of movement of molecules. We can calculate kinetic energy in physics. You have to. In chemistry, we don't have to actually calculate, okay? It's going to be 1/2 times the mass times the velocity squared. The more kinetic energy something has, that means that it's at a higher temperature. The molecules are moving faster. They have more kinetic energy. The temperature is higher. Opposite. The less kinetic energy something has, that means the lower the temperature. The molecules are moving slower. They have less kinetic energy. The temperature is lower. Here's the thing, though. 75,000 stars, like all the stars, if they're at the same temperature, they have the same kinetic energy. It doesn't matter what it is. It doesn't matter where it is. It doesn't matter if it's big, if it's little, if it's a solid, a liquid, or a gas. If it's at the same temperature, it's going to have the same kinetic energy. Identity doesn't matter. 100% on the AP exam. Easy point if you remember that. It's always true. It will tell you a gazillion things about it. It'll tell you molar masses. It's going to tell you that it's a solid. It's going to tell you all these things, and then it's going to say it's all at 273. How much kinetic energy do they have, or who has the most kinetic energy? Same. If it's at the same temperature, it's going to have the same kinetic energy. I need you to say it twice and hear it twice. Ready? Go. And by Monday, 50% of you are going to forget, and on warm-up, you're going to say it the wrong way. Let's watch. Okay. We have to draw a graph. I am redrawing this graph because, to me, hot is red and blue is cold. Is that the same to you? Hot is red and blue is cold. And they did it backward, and that, like, I can't think about it. So we are going to redraw this. This is called the Maxwell distribution graph. Maxwell-Boltzmann distribution graph. The Maxwell-Boltzmann distribution graph, a distribution graph is just like plotting a bunch of data points. It tells us if we had 100 molecules, what would they look like? So our x-axis is going to be kinetic energy, and our y-axis is number of molecules. Okay? Let's do cold first. So can you use your blue? At no point will something have no kinetic energy. That's called absolute zero. It does not exist. Yeah. Okay. So this is like a limit, an asymptote limit, where you get close but you can't touch it. Asymptote. This is an asymptote. Okay. It's not an actual thing. So if we had molecules and we distributed 100 of them, their distribution might look like this. I'm totally sketching. This is not quantitative. Draw a hump. Okay. So the most amount of molecules have a kinetic energy of this. Want to call it 50 because it looks like in the middle of mine. Call it whatever you want on your graph, wherever your hump is. Okay. Now let's draw. Let's call that 300 Kelvin. Let's draw a hot one. If I took data on 100 hotter molecules, their distribution might look like this. Move the hump over. How far? I don't know. Just scooch it to the right. So the most amount of molecules now have a kinetic energy of this. To me, that looks like 95. What this graph shows us is cold stuff has less kinetic energy than hot stuff. This is like actual data. This is the data to tell us that that's what's happening. We're going to write some words. Maxwell-Boltzmann distribution graph is the data to show that molecules at a lower temperature have less kinetic energy than those at a higher temperature. We didn't give the red, let's call red 400K, just so we're larger. Before you pack up, can you please talk about it with somebody? Talk about what the graph shows and why we scooched it to the right. Yeah, ready, go. Okay.